All right. So this is obviously something that we've done before, right? It's just graphing quadratic functions. And so the first one, we just have to take it piece by piece and we go, okay, what are our translations? It's erasing. Do I see that? It's like Harry Potter. Do you know what I'm talking about? Where it's doing that. Do you see that? Every time I write, it just erases.
Oh, it's the window. Okay, so just close one and reopen.
Close it and reopen it.
Sometimes it's too much for the tablet.
Close it up here.
Don't read my email.
Okay. There it all is. Dang it. Okay. Oh, okay. All right. Anyways, as I was saying, we first need to figure out our translations, which are what? What does that +2 tell us on the very end, right here? We're going to be going up 2. And then what's our other translation? What does this x + 3 tell us? Yeah, left 2. And then we know the general shape of this, right? What's my shape? Anybody remember what we used to call that? So you look at that cubed. Yeah, the John Travolta. JT. Shape of this is JT. And then the slope. How do we find the slope? Just that number out front, right? So 2, 1. 2 over 1. So then with all that information, I can just simply graph it, right? I don't need to even plug it into my calculator. So I can first find my reference point, and I can find that reference point by starting at the origin, because that's where the parent function started. Does anybody remember what the parent function of this graph is? So all of the parent function is right? Just x cubed, because that's what it looks like before any translations, any change of slope, anything like that. So anyways, if I'm graphing this graph, f of x, I start at the origin, because that's where the parent function would go through, and I go up 2, and left, how many? 3? Left 3. So up 2, left 3, and I go, okay, that's my new reference point. And so my general shape of a John Travolta looks like this, right? And I know my slope, so I just go up 2 over 1 and down to back 1, like that. And then I could just draw my graph in just like that. JT's. Well, this next one, g of x, this is actually easier than the last one. So the very first step is writing my translations. Which are what? What does that +4 tell me? Yep. So up 4. And inside the function, this tells me right 1. Because if it's -1, we go right 1. Okay, so this is a exponent of 2. So does anybody remember the shape of that? Yeah, parabola. Perfect. Shape. When I'm spelling that out in my head, I go parabola, because that's how it's spelled, parabola. Okay, and then what is this -2? Slope. So my parent function of this one, does anybody remember? Oops, g of x is equal to, what's my parent function? X squared. Super easy. That's my parent. So that just means it's the original before anything happened. Function. So my parent function goes through the origin like this. Remember? So now we're just going to apply our translations and our new slope and all that good stuff. Okay, so I start at 0, 0. And I know I'm going up 4 and right 1. So here's my new origin, or my new reference point, I mean. And I know my shape down, because I have a slope of -2, so it's down 2 over 1. Down 2 over 1. And then down to back 1. So it's going to look like that. Okay. So that's stuff that you guys were learning when I first came into the classroom at the beginning of the semester, was graphing quadratic functions. So today we're just going to do a new type of parent function, and this new parent function is 1 over x. So this is 8.1 graphing rational functions. So just like f of x is equal to x squared and g of x was equal to x cubed, we just have a new type of parent function, which is 1 over x. And actually this parent function works in almost the same way as the last one, meaning that the translations are going to look really similar, and it's going to be very similar to all that. So it's not too much new stuff. Okay. So the parent function is essentially just the most basic form of a rational function. Because just like x squared and x cubed, there was nothing that happened to it other than just that regular shape. So remember when we were talking about John Travolta's? We all knew that original shape. It always looked like this, right? And when you first saw that, were you kind of like, why? Like, why does it look like that? And we just learned, okay, well, that's just the shape of x cubes. Same thing with this. Its most basic shape is just that. Just a regular parabola. So rational functions, 1 over x. We could try graphing this. And this is just going to have a shape as well. The shape is going to look like let's try it out. Like that. And it's kind of hard to see. I'll zoom. Okay, so this gives us kind of a little bit of an idea of what's happening. So if I were to sketch this out, it would just look like this. So this is our shape. Of our rational functions. Has anybody ever seen this shape before? Okay. So let's just give some like observations, like what is actually happening with this graph? Let's look at the axes in particular. What's happening at the x-axis with both of those pieces? It never crosses it, right? So let's just make some observations. So never crosses x-axis. What else? What's another one? Never crosses the y either. So these are just some observations. Never crosses the x-axis and the y-axis. So, believe it or not, we have a name for when something never touches but gets closer and closer and closer. Okay? So these are called asymptotes. Asymptotes, that's how you say that. Asymptotes. Asymptotes. So, specifically in this case, since our graph never crosses the x-axis is an asymptote. Right there, because it gets closer and closer and closer but never touches. And so what would be another asymptote on here? Yeah, the y-axis. What are the equations for the lines of these? What's the equation for the line? What do we call that? Y-axis is what line? Y-axis is x equals 0. It's the line x equals 0. And I bet you can guess what the x-axis is. Y equals 0. So these rational functions are going to have an asymptote on the x-axis and an asymptote on the y-axis. Okay. So what do I mean when I say an asymptote really though? So an asymptote is a line. So let's look at this one, the horizontal. An asymptote is a line that a curve gets closer and closer to, but never touches. So this curve right here, we're getting closer and closer and closer to that asymptote, and this is going to go on and on and on forever and ever and ever, all the way to infinity. And even though we're just going to go on to infinity infinitely, we're never going to touch. It's just getting closer and closer and closer. So you can think of it like a string. If we had a string and we took half of it, we're getting closer. We took half of that. We can always take half of a string. We're always going to have a half of a string, even if it's the most finite, smallest amount. It could come down to a thread and then like a molecule. So there's always going to be something that we can take half of. So that distance essentially is being cut in half as we get closer and closer to infinity. It's just getting closer and closer and closer, but never touches. So same thing over on this side. We're getting closer and closer and closer to negative infinity, but we're never touching. Okay? And same thing with this, closer and closer, but never touching. So the asymptote basically stops it. We just don't cross over there. So then, if we already found our horizontal asymptote, which is the one that goes on the horizon, the horizontal asymptote, which we found was the x-axis. So this is our horizontal asymptote. So that's what we'll call that, HA, horizontal asymptote. And we already found our vertical asymptote. Then we can find our domain and range. So domain and range, we're going to be looking from left to right, this way, left to right. So we're going to be going, starting at negative infinity, going. Oops, we can't go there. So how do I write that? And then after that, 0, we can go on all the way to infinity. So we can write it like this. So our domain is going to start at negative infinity, start on that left side, and go to 0. And what does the parenthesis mean? It means it's not including 0, right? This parenthesis. If it was a bracket, what would that mean? Yep, and since it never touches 0, we can't do a bracket. We have to do the rounded parenthesis. Okay? And this means and. It looks like a U kind of. And from negative infinity to 0, then we can continue to the right-hand side, 0 to infinity. So we basically just have that break in 0, and we group them into 2 pieces. So how do you think I'm going to do my range then? My range is just starting from the very bottom and working my way up. It's my y values. So isn't there an asymptote right at y equals 0 too? So I just write it the same exact way, right? So starting down here at negative infinity, I'm going up. Oops, can't go past that. So I have negative infinity to 0, which stops me. And after I stop right here, I can go up all the way to infinity with my range. So 0 to infinity. So with this parent function, I found it had 2 asymptotes, a horizontal and a vertical right on the axes. And I could write my domain and range. Okay. So, you know how on those warm-ups, how we had an original parent function, and then that was the very first thing we learned when we were learning about quadratics. We learned the parent function, and then we started trying translations. So we learned our rational function, parent function, and now we're going to look at some translations. So this will be our first example. We had f of x is equal to well, what do you think that means? So you know how on a parabola, a parabolic function, we had f of x is equal to x squared? What if I went minus 3? Down 3. Same thing here. Just going down 3. Because this was our parent function, and it's on the outside. So our translation is down 3. And that's all that changed from my parent function. So then I can just graph that. So down 3, 1, 2, 3. So now instead of my asymptote being there, it's going to be right here. Then you just go across with your line. And then all you do from that is you just draw in your parent or your function just like you did the first time. Okay. Now we're going to again have a horizontal asymptote, a vertical asymptote, a domain, and a range. What's our horizontal asymptote then? We have a new one. It's this. But how do we write that? What is equal to -3? Y, yep, y is equal to -3. Perfect. And then what's our vertical? We didn't change that at all. So our vertical asymptote is still x is equal to 0, which is that line right there. X equals 0. This is y equals -3. So then we can just fill in our domain and range the same as we did before. So domain, we're looking at our x values, so we're starting at -infinity. Sometimes I write an 8. Does anybody else do that? I'm kind of slightly dyslexic. Okay, so we're starting at -infinity, and we're looking at our x values as we go this way, and we're going, but we can't go here because we have an asymptote, so we just write it the same way. Stop at 0, and 0 to infinity. That little u means and. So that's the same as before. Our range isn't going to be quite the same though. So range, we're looking at y values. So I'm going to start down here at the bottom towards -infinity, and I'm going to go up, go up, go up, go up, stop. What's stopping me there? My horizontal asymptote. But then from there I can just go on all the way up to infinity. So we can write this as starting at your lowest number, -infinity to what? -3, perfect. And -3 to infinity. Pretty simple, right? Okay. So we just went down 3 on that one. We had a vertical shift. And do you remember, let's look back at this warm-up really quick. Let's look at this first one. What horizontal shift did we have? Left 3, right? Left 3. And we knew that because inside of our function we had a +3. Okay? So inside we had a +3, so we knew we went left 3. So this will be second example. Which is f of x is equal to Does anybody know what's going to happen on this one? Left 5. Yep. Because it's inside of my function. Translations. Left 5. So can we do the same thing and graph it? Sure. So left 5, so I'm going to start by going 1, 2, 3, 4, 5. Bring my asymptote down. Once I have my asymptote, I can just draw my function the way I did on the first one. It's a little square. All right. In this example, what's my horizontal asymptote going to be? Uh-huh. And what about my vertical? Yeah. So then I could just write my domain and range after I have that figured out. My domain is going to be starting at negative infinity. That's going to go to what? Anybody know? Yep, negative 5. Because I'm going. Oops. Can't write that negative 5. Then I just continue. And negative 5 to infinity. Range is just going to be starting down here, going up. Can't cross that. And going up. So negative infinity to 0 and 0 to infinity. And this is interval notation. That's how you, have you guys seen interval notation? Yeah, when you're writing your domain and range. Yeah. So you guys are used to it. Interval notation. I like interval notation the best. Okay, cruising right along. So we had a vertical shift on the first one, and we had a horizontal shift on the second example. So what do you think the third example is going to be? Both? Okay, so what are my translations on this one? This rational function. Right 3, up 2. So there's my graph. I'm going to go right 3, draw my asymptote, and I'm going to go up 2, draw my asymptote. And then, just like we did last time, we just draw on our function. Just like that. List my horizontal asymptote, domain, and range. My horizontal asymptote, this is going to be y is equal to this function. Y is equal to 2. And now what's the name of this line? My vertical asymptote. Yeah. Yeah, there's another. So then my domain and range is pretty easy from there. Left to right, I start at negative infinity, my smallest number. And where does my domain stop? Where can't I go? 3, right? So basically I'm just sliding along here. Happy, happy, happy. Oops, can't cross that. So I can't cross 3. So then you would write 3. And then after 3, I'm okay. Go 3 all the way to infinity. So 3 to infinity. It's easy, right? So then my range is just negative infinity to, where does this one stop? 2. And 2 to infinity. You guys are so smart. My last class, their minds were like blown by this, so you guys are on top of it. So on these, every time you have to write your horizontal asymptote, vertical asymptote, domain, and range. Okay? So then just like on that warm-up example, like we had f of x is equal to 2x plus 3 squared plus 2 or whatever, and you know how that was a slope? Well, these can have slopes too, and what they look like and this is going to be our last example. So what they look like is, let's call this g of x is equal to x, oops, not that, 4. Actually, I'm going to do the first problem on the worksheet, or the second problem on the worksheet for the homework today, just so that the people who aren't here for basketball can see an example. So let's do, I guess you guys don't have it yet, but this will be number 2 on the worksheet. Okay. Example 4 is number 2 from 8.1 worksheet, and we are graphing the function, identifying the translations, vertical and horizontal asymptotes, and domain and range. So exactly what we were doing last time. So this one says 2 divided by x minus 3 minus 1. Alrighty. So what are my translations? Yep. Right, 3. So that's a 3. Down 1. And then I have this 2. So let's see what that 2 does to it.